title of my talk today is the same as the research study that we just recently published in ESMT earlier this month, called Home is Where the Pipeline Ends, Characterization of Volatile Organic Compounds Present in Natural Gas at the Point of the Residential End User. I don't have to introduce myself or PSE because Colin just did a great job of that. So let's dive right in. So this is a methane talk, so a little bit of motivation from the methane side. So this study came out early last year and was really influential for us in thinking about downstream methane emissions. So, this was a really rigorous study. This was about 8 years of continuous sampling. They had, 5 different Picaros going at once, 2 within the greater Boston area, 2 upwind. They were able to do some high split inverse modeling and really kind of pinpoint just how much of a methane flux is coming from, an old leaky city like Boston. So, I mean, the numbers are, I'll just read here from the abstract because, the numbers really are pretty startling. So they estimated by these methods that up to 2.5% of the natural gas delivered to a city like Greater Boston is lost. So, this is effectively doubling, conservative estimates of the upstream midstream. So, their final number was, 4.7% methane emissions in the entire natural gas supply chain, which from a climate standpoint, I think we all know what a number like that means. So the other really important study that came out, which I think Eric and Colin, I think you gave a meta talk a few months ago, but this was really important for us in thinking about stove emissions. And so, what the really surprising finding was here is that all stoves and ovens leak a little bit when they're just sitting there. This is basically a plot of every single stove that they measured. And when you add these up, the emissions are non-trivial. They're certainly not as much as other appliances, but as we'll talk about in a little bit, they're really important to think about because of the folks that we talk to when we perform our studies, it's really this is the most familiar appliance. People understand cooking with a gas stove and so forth. So, but yeah, really just kind of hone in on this. The steady state off emissions. They were 75% of the total emissions. This is in part because the stove is predominantly off, but really important for us to think about. If we want to characterize what else is in natural gas, here we have a potential exposure route that is pretty chronic, potentially pretty chronic exposure pathway. So again, the backdrop here is really important so I'm a public health practitioner, think about public health in addition to, climate change. And so, what's different here is, really this is the only appliance in the home that is not automatically vented. So you have to manually vent it. This is essentially located part of the home. Anything coming out of here, whether pre-combustion, post-combustion, is going to have a high intake fraction in terms of, how much of that source of pollution we are breathing into our lungs. We take about 20,000 breaths per day, spend, upwards of, I don't know, the whole darn day inside anymore. So yeah, this is a important potential source of both climate and health damaging air pollutants. And so the other literature I want to bring in here, which is really how I got my start in thinking about extractive industries and health, is really looking at what are the health impacts associated with living around extractive industries. And this is like pretty much scientific consensus at this point. There's multiple health endpoints that have been statistically significant, in multiple different basins. So, there's really a rich science here in thinking about exposure to extractive industries and health. Now, of course, a lot of these health effects are multi-causal. We're dealing with multiple different exposure pathways, even, other things that are much harder to measure, like psychosocial stressors that are mediating probably, a fair amount of this harm. But one common thread here for sure is there's an air pollution pathway happening here to some degree. More so for some health impacts than others, but certainly air pollution is a really big factor here. So, back to this backdrop, one thing we've been thinking about is really this is the end of a pipeline. If those extractive industries are, these heavily industrialized areas, pipelines are effectively, an extension of those industrial activities, vis-a-vis the hydrocarbon that is, being transported from those locations to, inside our homes. So, from a methane standpoint, we kind of just throw around what is natural gas, oh, it's mostly methane. And from a climate perspective, totally reasonable. It is mostly methane. But from a health perspective, that's not totally helpful. I mean, we kind of need, what else is in natural gas? And so, that was exactly the research question we set out to ask. Now, of course, we're not the first ones to ask what is in natural gas, unprocessed natural gas, decades of study of, trace gases, inorganics, there's a long research of that. Even research in looking at healthy imaging air pollutants present in other portions of this natural gas supply chain, which you can think of, we're starting to get to more processed gas, and still finding healthy imaging air pollutants. This was a systematic review in 2020, but really the study here, my point is this stops short of the end user. And so really this is the crux of our research question, is really trying to figure out, are there other healthy imaging air pollutants present in the hydrocarbon stream at the point where we use it, knowing that leakage is probably occurring a lot more than we think and around where people live. Okay, so how do we do this? So pretty standard, air quality measurement techniques. EPA method TO15, been around a long time to look at trace volatiles in different matrices. ASTM D1946, also been around a long time. Most notably, we use that for getting methane and ethane in our samples, which of course is really important if we want to know whether or not if we sufficiently captured a sample from a gas stove. So as you can see here, kind of walking through the steps, we are literally attaching a hose to the end of a pipeline, taking a sample. And also mentioned there that we measured the odorants in natural gas, which we'll get into. And of course, here's my current colleague, former Stanford grad, Eric LaBelle, taking a sample. So you can see here, direct line connection. We don't want any ambient air intrusion. Teflon line tube going into a passivated cyanide line canister. And these are 0.4 liter canisters. The sample takes about 30 seconds, given the flow of gas from a typical stove, so it really doesn't take long at all to get a sample. We get information, depends on the lab you use, about 300 different chemical compounds, many of them isomers, but yeah, this was the data that we collected throughout Greater Boston. That's the setting for the study. So you'll see here the black dots are our unique sampling locations. After doing a bunch of QA/QC, we had 69 unique locations across 15 different communities in Greater Boston, led to 234 sufficiently captured samples over a 16-month time frame. So we certainly had some repeat samples there at unique locations to kind of get a sense of temporal variability of trace volatiles over time. The Boston is a little bit unique in the sense that it has 3 gas companies pretty close by. It doesn't anymore. When we did, it had 3 gas companies. Columbia was bought out by Eversource after the Merrimack Valley incident. So everything orange is now yellow. But at the time, we wanted to equally sample across the 3 different gas companies, not knowing if gas distributors mattered, either in terms of how they're supplying their gas, how they're sourcing their gas, or the odorants they're using. We really didn't worry about anything else in terms of equitably sampling. We tried to sample around the 3 different pipelines. Those are the the different colored lines here. 3 major pipelines that flow into Greater Boston, supply Greater Boston with natural gas. But we found out it's really hard to figure out, where a home is versus the pipeline that it's potentially getting its gas from. Much likely, it's a mixture, and there really are a lot of pipelines if you, start to look at the street network. So it's kind of a mess. Even found out that the Maritime pipeline can actually has bidirectional flow, which is not uncommon there. So kind of tricky to do source apportionment here. But so that's our sampling suite. We'll dive right into results. Again, published earlier this year in ESCT. So I'll lay out like our 3 major findings, and we can dig into each one of them a bit more. So the 3 major findings was natural gas used in homes contains trace amounts of numerous air toxics. Looking at the odorants, we found that small leaks can certainly be odorless. And kind of our culminating result or conclusion is leaking natural gas we know is impacting the climate. Maybe we should also be thinking about direct health impacts through impacts to air quality around those leaks. So dig right in. So we found 296 unique chemical compounds across our sampling suite. 21 of those are characterized as hazardous air pollutants, HAPs. So that's a special EPA classification of air pollutants that are known to cause cancer, other serious health effects. There's 187 of those compounds on that list. So we detected 21 of them in gas. We didn't check them in every sample, but 21 of them were detected. Now, these concentrations are actually pretty low. So the non-methane VOC content, the total mean non-methane VOC content, 6 parts per million was our mean. This doesn't include ethane. So the concentrations are pretty low, but so in our study, we really, thinking about the health impacts, we really, we focused on benzene, one of the aromatics. It's pretty toxic, really drives a lot of the risk assessments of indoor air quality. Again, this concentration is pretty low. This is a bootstrap mean, 164 parts per billion, but we did detect it in nearly every sample, and we could talk a little bit more about what this means. But so here's our table 1. The top 10 VOCs. This is probably not uncommon. We do get information on some of these trace gases in natural gas postings at midstream pipelines, but some of the heavier stuff is not necessarily individually speciated. You'll get the C6 plus fraction. So this is really kind of disaggregating that C6 plus fraction, giving us a sense of what kind of concentrations are in gas at the point where it's delivered to our homes. Also notice here that our methane ethane really good. I mean, we were capturing 100% natural gas. It's pretty undebatable. So the kind of first surprising finding was we actually found pretty significant fluctuation of these trace volatiles in natural gas across the different Boston communities and the 3 different gas companies. So if we break this out a little bit, we did see that Columbia Gas, formerly Columbia Gas, had slightly higher BTEX. It was significant, but not by much. If we dug into this data a little bit more, and we actually found that it's not really gas company, it's really location is a much more important contributing factor. Gas company maybe doesn't even matter. Maybe that's a second order effect, or it's just proxying for gas supply. Maybe it's proxying for pipeline. So yeah, this is the Merrimack Valley region, this little island. So, I mean, this was certainly an important finding, and we've kind of taken this finding to heart and really trying to figure out how important source of gas is, how much variation there is, then probably probably between city is probably a more important kind of question to ask, and so that's what we've been doing. We've actually been performing similar sampling like this in a lot of different other U.S. cities to really try and get a sense of, okay, if this doesn't seem to be ubiquitous, there seems to be, important spatial variations, what are potential root causes? Because here we really couldn't get into root cause too much. Just didn't really have the understanding of gas supply to really go much further than being descriptive here. So even though we found significant spatial variation, I mean, the temporal variation was much higher, much greater. We found this seasonal winter peak that we observed twice in successive winters. This winter peak in terms of, we'll just talk about benzene here, was 3 times higher in the winter than it was in the spring in end-use natural gas, and it's 8 times higher in the winter than it was in the summer. So really pretty big fluctuation here. So here we're looking at benzene again over time. You'll notice we were one of the studies that made its way through a COVID pause of no longer doing any sampling for a period of time. And then actually a lot of these are actually sampling building risers, so outdoor gas grill connections. We still did have some stoves in here, but a lot of outdoor gas grills. It's the same, we did some sensitivity tests, it's really the same gas. But so really take home messages here, we really see the concentrations peak around, the late winter time. And really just kind of coinciding most likely with more energy use, more natural gas use in the winter. Boston is pretty cold in the winter time. But again, really difficult to kind of get a root cause here. Is the source of gas changing? Not sure. Something else going on? Not really sure. But it's important that we're finding differences that are in the wintertime versus other times in terms of health impacts. We can talk a little bit more about contextualizing what that might mean in a little bit, but yeah, that's the temporal variability. So, and I'll just say, I'm using benzene as kind of like the case study here, but a lot of these trace volatiles, they're heavily related. So benzene's high, total, the total non-methane VOC content is high. There's a little bit of deviation there and some important molar ratios that we did look at, but really focused on benzene here. So next we thought, okay, well, what does this mean in terms of contribution to air quality? We really wanted to get into this question in indoor air. That was the setting that we collected these samples, but we found that this our work kind of predated Eric's work, so we really didn't think about using emissions from steady state off stoves. We're doing that now, but at the time, what we really had only to go by was urban level downstream natural gas methane emissions. So we had fluxes of methane emissions. So actually in Greater Boston, there had been 3 studies done to date, estimating how much of the kind of urban flux of methane is released in a year. So these are these estimates in kilograms per year. So simply we did some pretty simple math. We used our molar ratio of what we found in end-use natural gas of our BTEX concentrations to the methane concentrations that we found, adjusted for molecular weight, and we were able to estimate an equivalent urban scale BTEX flux. So these are the co-emissions alongside the natural gas emissions, assuming that methane is a perfect proxy for natural gas emissions. If natural gas is 99, 98, mid-90s, methane, it's a pretty fair assumption. And so, to put a little context on these numbers are just kind of out there. They are pretty low in terms of other benzene sources. I mean, benzene is still heavily transportation, both vehicle and airplane emissions. Gasoline, obviously, I mean, gasoline can be up to like 10% benzene. So, those fugitive emissions are still pretty large. But that being said, this is a source of benzene in urban areas that is not included in any inventories. So the kind of two ways we contextualize this is what, you're getting more benzene from natural gas leaks in a place like Greater Boston than you're getting from the estimated, EPA inventory for how much benzene is released from combusting natural gas in the residential sector. Again, it's not that much. Maybe this is because, we don't really know how much benzene is coming from post-combustion methane in some of our common appliances. But so one way to contextualize. The other way to think about it is, this benzene level, these three different estimates across these three different studies is, it's about 10% of all of the light-duty vehicles in all of Massachusetts. So again, a pretty small, marginal source of benzene, but it's benzene nonetheless. And I know, we get in this habit of, talking about, single pollutant emissions, but like I said, there's a lot of other, there's a lot of hexane in here as well. A lot of other, trace gases that are, secondary, contribute to secondary formation of ozone and PM. So yeah, certainly something to think about in terms of contribution to outdoor and indoor air, which we certainly need to continue studying. So hop over to kind of our next line of inquiry, which actually has probably more relevance in terms of a methane focused audience is we actually didn't really think of this early on, but then it kind of turned into like a kind of an important analysis where we actually wanted to show at what level of a leak could you have in these urban areas that could go undetected? That is, it doesn't have an odor. We're seeing these studies that are estimating concentrations of leaks that, seem like they're pretty high. I mean, if you've ever been to Boston, it certainly doesn't take long to smell a leak outdoors. I mean, there's a lot of leaks happening in cities, but there has to be a concentration at which odorant level is not high enough, and there's an equivalent methane amount of leakage happening without our noses able to detect it. So just to catch everyone up to speed here, natural gas, mostly methane, completely odorless. If they didn't add odorants, we wouldn't be able to detect it. It's been an absolute windfall in terms of public health and safety, and it allows us to use natural gas to the degree we do, as a commodity. It's literally probably sitting next to most of us in our homes, and so it is the it's the only really line of defense for a gas leak, but it actually works really well. What we think, kind of what we're trying to get at here. So here's a person. This is perhaps a bit outdated, but they do they have humans out there smelling and use natural gas to determine if it's effectively odorized. And so when you start to get into the numbers of how much odor is added to natural gas, it's not really a straightforward. You can't really get a good solid answer. I mean, some of this is proprietary business practices. They're using odorant blends, and just to mention these odorants, they're sulfur compounds, they're thiols. Our noses are actually really sensitive to these compounds. It's probably in part because our ancestors evolved a long time ago to smell rotting meat, and that's really harmful. And so we're left over with this really sensitive ability to smell these compounds. And so so let's talk about how much odor is added to natural gas in terms of what we do know. So first of all, just gives a sense of methane is only flammable in this little Goldilocks zone. So here's like a bar. Here's 100% methane, right? Methane will only ignite in between a 5% and 14% ambient concentration. So if it's not up to 5%, there's not enough methane molecules to combust. If it's greater than 14%, there's not enough ambient air to sustain a flame. So when you actually look at what the Code of Federal Regulations are for odorization of natural gas. It's actually a little bit concerning because the level that they state is, a natural gas distribution line has to be odorized so that a concentration in air, that is a leak, is detectable at 1/5 the lower explosion limit. We won't get into what a person with normal sense of smell is because I don't know if we could define that, but this is effectively 1% natural gas. So as per the Code of Federal Regulations, natural gas flowing into our homes, our streets, only needs to be odorized to the point of 1% if in the presence of a leak in ambient air. This is actually a pretty high concentration. I mean, it would certainly, if gas was actually odorized to this level, and this meaning like everything below 1% is potentially non-detectable, it certainly would support some of the studies. Of course, we aren't smelling, these lower kind of level of leaks. But so really was, the research question that we had is because we were measuring how much odorant is in natural gas at the point where we use it, really trying to figure out, within this box here, what is the equivalent methane leak rate that is odorless, given the odorant concentrations that we found. So that's really the question. Trying to figure out, is it closer to 0 or is it closer to 1%? So the two odorants that we frequently detected in our samples were tert-butyl mercaptan and isopropyl mercaptan. These are pretty standard. Tert-butyl mercaptan, we've been doing sampling in other cities. It's pretty much used throughout the US, probably North America. There are certainly blends. There's other odorants around, but TBM is really the one doing most of the work here in terms of its odorization. So these are bootstrap mean concentrations. So next, to kind of answer this question, we need to know what is the odorant detection threshold for these compounds. So the way to think about that is, at what concentration of tert-butyl mercaptan in the ambient air would your nose be able to detect? Like, I smell that. So what we're actually looking here is, it's kind of crude how they do these panel studies, but effectively, it's a panel of 10 people in a room. They put various concentrations of, in this case, this odorant. They do this for other chemicals as well. And it's the point at which half the people in the room can smell or can detect the chemical. They determine that to be the odorant detection threshold for that compound. Now, this is a relatively new paper. It's actually it's a preprint. This odor detection threshold is actually really conservative. Some of the older work had odor detection thresholds much higher than this, around 0.3 parts per billion. We use a really conservative odor detection threshold. Taking into account this new science, they use much better, I think, controlled. A much better controlled study here in terms of estimating what is the potential odorant detection threshold compound. So we do a little bit of math. It's simply kind of rearranging this odor detection threshold, the concentration of our odorants that we get in gas, the amount of methane, and we determine that a leak of a mean leak of around 21 parts per million methane equivalent is potentially undetectable by, if you want to call it, 50% of the population. So it's not 1%, thank goodness. It's not 0. So I mean, having been out in quite a few homes, a couple hundred homes at this point, we do find leaks. They happen. They are happening in homes. People sometimes don't. I sometimes can smell it right away. Sometimes my colleagues can. And sometimes there's a lot of competing smells in the home. Cooking someone, there's pets. I was honestly surprised how often folks are living with a leak and don't know it. So even though we're kind of fixating on this odor detection threshold, there's a huge variation in the general public in terms of their sensitivity to these compounds. It's estimated that like 1,000x variation in the general public. we generally lose sensitivity to all kind of odors as we age. So there's certainly an age component here. The other thing on the other end, we did find large variations of these odorants. Now, there's certainly a limitation to the odorant data that we collected. We didn't use the kind of the standard method. We're doing that now. So certainly these data have a caveat, but the detections, we found TBM in 95% of our samples. We're using cyanide line canisters, which are suitable for sulfur compounds. So, we think this is a reasonable first guess. Oh, and also here, this interesting butterfly effect of, people suffering from various degrees of anosmia, unable to smell from things like long COVID. So certainly something we're thinking about in terms of, health and health and safety, being able to detect a leak or not. And so alongside kind of that variability, there was also a trend of variability, kind of the opposite of what we would want to see. We actually found lower odorant levels in the wintertime. Really, again, unsure why this is. And it's kind of the opposite of what we want. If we're using more gas, potentially more gas is being leaked in the wintertime, we're finding higher concentrations of the trace volatiles that we don't want to be breathing in. We don't want to have a lower odorant concentration, because that effectively means if the odorant level is lower, the undetectable leak level is effectively higher. So again, one of those kind of surprising findings. And the take home here is maybe small leaks are occurring behind the meter, and maybe a lot of these smaller leaks can and are adding up to potentially large amount of gas in cities. So, quickly back here to the downstream methane leakage study. So, I mean, if you look at the Washington Post article, I didn't mention this before, but the headline was actually, they estimated a lot of this is potentially coming from inside the home, and this was because they found this really interesting association with consumption, finding that again there was a lot more leakage in and around the city from their their measurements during the wintertime. And so they associated with this consumption, and then associated with, well, what's fluctuating during the year? It's appliances. Appliances are being used more, cycling on and off more. They also did they also had like an interesting kind of, quasi-natural study with COVID as well. They saw concentrations of methane leaks went down during COVID, again, kind of confirming that, there's some kind of association with gas use and leakage. So this was, I just pulled this out because it was an interesting quote from Eric Court here. And, if we're going to say concentrations are leaking from inside homes, the common conception is, we should be readily detecting it. Like, this is kind of the common conception. If there's a leak, we're going to smell it. And I mean, I think that requires, a bit more thinking, kind of just beyond the, the empirical data that we're showing. There's a lot of reasons people might not report a leak. We experience this. If you're a renter, you don't want to talk to your landlord potentially for multiple reasons. There's a lot of potential reasons, especially in cities, why, behind the meter leaks could be occurring. And so I certainly think this is a place to really think about, the nexus of climate and health. And yeah, really thinking about, natural gas as kind of, this emerging place to really discuss these issues. So, I'm kind of wrap up here. And so we know that leaking natural gas is impacting climate. It's a lot of great research that's coming through. But, the health has really kind of focused in the upstream, really hasn't, emerged outside of that. But yeah, I think with, some of the emerging studies around combustion, around gas stove use, other appliances in homes, yeah, maybe we should also be thinking about more direct air quality impacts in health. So, kind of the caveat here, this is just a hazard identification study in kind of the risk assessment paradigm. Really, we would go the full way and actually estimate, what are the potential human health risks associated with, the things that we are seeing. I kind of draw, analogies to kind of what's happening in kind of the PFAS world right now, where we're really just trying to figure out where all PFAS is. We know PFAS is pretty toxic. So we know some of these, compounds are toxic. So really, we were just trying to figure out, okay, what's in gas at the point where we use it. We need to do the exposure studies. So that's, thinking about, Eric Labelle's work and thinking about, how much are stoves leaking into our indoor spaces, how much post-combustion as well. Those are kind of the exposure studies that we need to do next. Let's get to that point of estimating health impact. So yeah, but I think what we can say is, this is a relatively unaccounted for exposure pathway indoors and outdoors, of these trace volatiles that are, directly, health relevant and are contributing to, urban contribution of other pollutants, ozone and PM. And so, I mean, thinking about this as additive, additive to any of the post-combustion pollution that we study a lot in certainly in outdoor air and much less in indoor air. And so, yeah, I mean, I think in terms of like thinking about more research, if the wintertime, at least in Boston, finding that, for whatever reason, some of these trace volatiles are higher in the wintertime, we're using gas appliances more so there's more leakage. We spend more time indoors in the wintertime. There's certainly less ventilation. And, thinking about, as we're transitioning to heat pumps, I mean, heat pumps are not bringing in outdoor air. It's recycling indoor air. So really thinking about these indoor sources of pollution are it's really important. And, we really don't know that much about indoor air when you compare it to how much we know about outdoor air. So, and so, yeah, I mean, kind of thinking about the methane implications here in terms of like, how do we think about, we focus on, methane from landfills, methane from wetlands. But, I think if there's co-pollutants, they're commingled within, the hydrocarbon stream itself. It's kind of making distinct. I mean, certainly from, I think, agricultural emissions, I think landfill emissions, there's certainly, there's other trace pollutants in there as well. But, if we're comparing one to the other, put this in the column that, would tip the scale towards, addressing this source of methane first, all else being equal. So really kind of high level, just conclusions and recommendations, because we try and do science and policy here. So thinking about, okay, what is it, if our end use natural gas contains, very small amounts of VOCs and hazardous air pollutants, what are the recommendations along that? Well, as I mentioned before, this is a largely unaccounted for source of urban non-methane VOCs. It's not in inventories. We inventory much smaller sources of a benzene, for instance. So there's no reason why we shouldn't be inventorying these sources as well. I think operators here, local distribution companies, they have readily access to their product. I mean, we could push for more stringent reporting of these detailed compositions of natural gas. Reporting individual compounds, semi-regularly. Also they could perform, similar sampling to us in terms of these compounds, actually sampling at the point where we use gas, not necessarily upstream at the point where, they deliver it. And, another way to kind of think about, I kind of mentioned this before, but, these co-pollutants on the flip side, they're a co-benefit of, fossil methane reduction. That's kind of the way we think about it from a policy standpoint. And so those costs should also be included when we do our cost benefit analyses. So with the odorants, yeah, I think we need more study here. I think certainly this warrants more study. One thing we could think about doing, if we know that, these odorant compounds are completely benign and do not have kind of, low dose, chronic health effects associated with them, they are chemicals in themselves. They're pretty toxic, not toxic, but, they're potent in terms of their, their ability to, antagonize our sense of smell. So, but perhaps maybe just increasing the odorant level in, downstream natural gas is that a way to kind of, get us more, capturing some of these smaller leaks potentially. So that's one idea. Like I mentioned, the Code of Federal Regulations, I mean, those regulations were, they were done in the 70s. I mean, we could really think about, lowering those odor detection requirements. It could be a much lower threshold than, effectively 1% methane equivalent. Actually, the Commonwealth of Massachusetts has a lower level. So, states do have the jurisdiction to think about odorization. And certainly, yeah, thinking about, in-homes leaks, we need better survey tools for these smaller leaks in homes. Like bringing a CGI into a home, you're not going to capture these smaller leaks. You really do need, you need better instrumentation. So there's not an easy fix here. Maybe increased odor is a, one kind of more pragmatic way to think about. But again, yeah, there's certainly more that needs to be done, and really the only way to get rid of this source would be to remove it entirely otherwise. So yeah, we have a lot more to learn about gas and health for sure. Certainly calling for more research, indoor air quality, pre-combustion and post-combustion products alike. I think, yeah, we probably need to think about some other microenvironments here in thinking about, gas leaks and occupational settings. I mean, yeah, the whole way up the entire supply chain, getting back to like, proximity of living around extractive industries and emissions. So, a portion of this leakage that occurs in some of the midstream compressor stations, blowdowns, yeah, what do we actually know about, trace volatiles being released from some of those events? Other occupational settings, I'm thinking about like commercial kitchens, where you have, a lot of different gas appliances going for a very long period of time during the day. That's an interesting microenvironment to think about. And kind of the last note is here, we only really know what we measure. We're only just measuring what's kind of easy to measure, these kind of trace volatiles, which we kind of knew they were going to be there to a certain degree, but there's kind of other classes of chemicals we might want to be thinking about as well. Radioactivity is kind of interesting, heavy metals, there's PCBs in a lot of these old pipelines. It's in liquid form, but yeah, I think we're certainly thinking about other suites of pollutants here as well. Same goes for post-combustion as well. So that's all I have. I just want to thank my great team that I've, great pleasure to work with over the years. And for more resources, here they are. And that's all I have. And I'll stop sharing and we can take some questions.